Hi gentlemen, these will be your Unit 0 Day 5 notes. Again, if you would like to see the warm-up or review question or any homework questions we covered today, just look at the finished notes. So today we're going to talk about exponential functions, their graphs, their properties. We'll talk about exponential growth and decay. We'll talk about the properties of exponents and how to simplify expressions using exponents. And then we'll talk about the inverse of exponential functions, which is the logarithmic function. We'll talk about their properties, and we'll talk about how to solve both exponential and logarithmic equations. So an exponential function is any function where the variable is the exponent. So the variable is the exponent in an exponential function. So if you had y equals 2 to the x, I believe that's the parent function we did on the parent function worksheet. So if you had y equals 2 to the x and you wanted to graph that, 2 to the 0th power is 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the negative first power, remember if you have 2 to the negative 1, you bring it to the denominator, and this would be 1/2. 2 to the negative 2 power would be 1 over 2 squared, or 1/4. And so your exponential functions look like ramps. They start off really small, and then they get really big as you start growing. So their y-intercept, if you don't move them up or down, remember anything to the 0th power is 1, so their y-intercept on the parent function is 0, 1. There are no x-intercepts on the parent function. If you moved the graph up or down using transformations, it would have an intercept, but for right now, it wouldn't. This is exponential growth because my graph is growing. To do exponential decay, you've got two options. You can do 2 to the negative x, and that would look like this. Or you could do like 1/2 to the x, and then it's growing smaller as you go along. So the domain and range of an exponential function, so again, if we look at this guy, domain is your x values. So the domain, notice, is there's no breaks in my graph, there's no asymptotes, there's no holes. So my domain is going to be all real numbers, or the x values can go from negative infinity to positive infinity. The range of the parent function is that my y values start really close to 0 and then they climb to infinity. So my range would go from 0 to infinity, or y is greater than 0. So exponential growth. So these would be bacteria problems, population problems, things like that. The most basic way of thinking of exponential growth is you have your original amount, so whatever you're talking about, bacteria, money, and then you are going to raise that to the multiplier, times that by the multiplier raised by the number of times it's doubled or tripled or whatever it's happening. And that's going to equal the new amount. So in the interest formula, you can say the amount is going to equal the principal times the interest rate, right? So it's 1 plus the rate over n to the nt. That's the compound interest formula. And that's what banks use. And so remember, R is the rate as a decimal. T is the number of years. And N is the number of times it's been compounded per year. So it could be compounded monthly, quarterly, yearly, weekly. So that is one of the formulas. Or if it's not, you could also do simple interest. So the final amount is going to equal the original amount, which is P, and then 1 plus the rate, or minus the rate if you're getting less in value, like if your car is depreciating in value, and then raised to the T. So let's look at an example of these. The population of Silver Run in the year 1890 was 6,250. Assume that the population increased at a rate of 2.75% per year. So 2.75% as a decimal, remember move it over twice, would be 0.0275. Estimate the population in 1915 and 1940. So in 1915, the new population A would be the original population, 6,250, times the rate, and this is just simple interest, so it's going to be 100% plus the new rate, 0.0275, and then raised how many years have gone by between the original population of, the original year of 1890 and the new year of 1915. That would be 25. And so my amount's going to be 6,250 and then 1.0275 raised to the 25. I don't have a calculator on me, but you're going to do order of operations first. You would multiply this first, and then whatever you get, you would multiply by 6,250. For the year 1940, you would do the same thing, but this time, what would the year be? Instead of 25 years, we would have 6,250, and then 1.0275 raised to the number of years between 1890 and 1940 would be 50. So you guys can check your work against the finished notes to see if you got those two right. When did the population reach 50,000? So we want our final population to be 50,000. And so we have 50,000 to be the final population. And then the original population was 6,250. And then we have to the 1.0275 and then raised to the t. We're going to solve that for t. So if you guys remember how to do this, or you can guess and check at this point in time, you're going to have to use logarithms to solve this. So we'll come back to this problem after we relearn about logarithms. Exponential decay is when your amount is going down in volume. So for instance, you can have your original amount, and then you would have you would have the final amount equals the original amount, and this time you would do the 100% of the original, and then since it's decay, you're going to subtract the rate and then raise to the t. So let's look at an example of exponential decay. Suppose that in any given year, the number of cases of a disease is reduced by 20%. So we're going to take away 20% this time. There's 10,000 cases originally. How long will it take to reduce it to 1,000 cases? So we want 1,000 cases to be our final, and that's going to equal 10,000. And then it's the original 100%, and 100% is 1, minus 20% as a decimal is 0.2, so minus 0.2, and then we want to know how long that would take. So again, we're going to have to learn about logarithms again. So we'll come back to this problem once we learn about logarithms, and so we're going to have to solve that equation to t. How long will it take to reduce the number of cases to less than 1? So we want 1 to be greater than or equal to, well, I guess less than 1, just greater than, and then our original case is 10,000, and then 0.8 raised to the t. So again, we'll come back to this problem after we learn about logarithms. Properties of exponential expressions. Hopefully you guys remember all the properties of exponents. You've got the product property, and that tells you if you multiply two things with the same base, so x to the second times x to the fifth, you can add their exponents, and this would be x to the seventh. You have the quotient property of exponents. So if I had x to the eighth over x to the fifth, you subtract their exponents and you would have x to the third. If you had a negative exponent, like x to the negative fourth, that is the same thing as 1 over x to the fourth. And that just comes from the quotient property. So if I had x to the fourth over x to the eighth, the rule is subtract their exponents and you would get x to the negative fourth. But notice there's more x's left in the denominator. That's why you would have 4 remaining in the denominator after you canceled. You also have the power property of exponents. So this is if you're taking an exponential expression and you're raising it to a power, you can multiply those exponents. And so this would be x to the 12th, or you could write it x to the 4th 3 times, x to the 4th, x to the 4th, x to the 4th. And in this case, you would add the exponents and you would get x to the 12th. Something to remember, if we had 3x to the 5th and we want to take that to the 3rd power, every term on the inside is raised to the 3rd power. So this would be 3 to the 3rd, which is 27, and then x to the 5th to the 3rd would be x to the 15th. So rewriting and solving exponential expressions by changing the bases. So this is how you can solve exponential expressions if you can create two terms that would have the same base. Like 32 raised to the 2x minus 4 is going to equal 8 to the 3x plus 2. So 32 and 8 are both powers of 2, so I can rewrite them as powers of 2. 32 is 2 to the 5th, and then we are raising that to the 2x minus 4 power. And then 8 is 2 to the 3rd, and then we're raising that to the 3x plus 2 power. Notice now that they have the same base, we can just set their exponents equal to each other. So we have 5 times 2x minus 4 has to equal 3 times 3x plus 2 for this expression to be the same. So distribute 10x minus 20 needs to equal 9x plus 6. So x is going to have to equal 26 for this to be true. And you can always plug it back in to see if it works. So gentlemen, go ahead and see if you guys can solve A. 3 raised to the 2x minus 4 power equals 27 raised to the x plus 1 power. And then for B, you're going to have to combine these two first using the product property, and then you're going to want to get the same base. So this is 2 to the negative 3y times, and then I'm going to change 8 to 2 to the 3rd times 5y, and then I'm going to change 32 to 2 to the 5th power, and then times 4y. Remember, if you're multiplying things with the same base, you can add their exponents. So this would be 2 to the negative 3y plus 15y equals 2 to the 20y. So see if you guys can solve those two, and then you can check your work in finished notes. We can also solve exponential equations graphically. So if I had 5 to the 2x minus 4 equals 17 to the 3x plus 1, and I wanted to know what would x have to be, we can just go on Desmos and we could graph the first one and then graph the second one and see what happens. So this is 5 raised to the 2x, and I think I need to put it in parentheses so it'll stay up in the exponent. So 2x minus 4, there's my first one. And I want that to equal, and then I'm going to graph the second one, 17 raised to the, and I forgot what the exponent was, 17 raised to the 3x plus 1. So again, parentheses for that exponent, 3x plus 1. And my solution is going to be where those two intersect each other. And notice Desmos was giving that point where they would intersect each other. And so my solution is negative 1.756. So that would be where those two graphs would intersect each other, I believe. Yeah, that's the point that they're giving. So that's my point of intersection. So to find their solution graphically, you graph both and find their intersection point. Logarithmic functions. So to find a logarithmic function, it's the inverse of an exponential function. So a logarithmic function would look like log base 2 of x. And so graphically, what that looks like is the inverse of an exponential graph. So he looks like this. And remember, inverse graphs are reflected over the line y equals x. So for a logarithmic function, you're just switching all of the x and y points on the exponential graph. Now notice for the domain of a logarithmic function, his domain is x is greater than 0, or x can go from 0 to infinity, and that's the reverse of the range of a exponential graph. And then the range of a logarithmic graph is everything. So all y values exist on a logarithmic graph. Properties of logarithms. So you guys might remember some logarithm properties. If you have two logs and they have the same base, like log base 2 of 4 plus log base 2 of 7. If you have two logs and they have the same base and you're adding them, you can multiply the two products together. So this would be log base 2 of 4 times 7, which would be the log base 2 of 28. That's one of our log properties. Another log property is if you were subtracting them, log base 2 of 4 minus log base 2 of 7 you can change this into 1 log by dividing them. So this would be log base 2 of 4 over 7. If you have a logarithm that has an exponent, like log base 2 of 4 raised to the 5th power, you can take that exponent and bring it to the front. So this would be log base 2 of 4 to the 5th. So this would be log base 2 of 4, and that 5 can come into the front. Because remember, this would be log base 2 of 4 times 4 times 4 times 4 times 4 if you wrote it out. And then remember, if I have two logs, if I have a log base 2 and then two guys being multiplied together, I could separate it back out with addition. So this would be log base 2 of 4 plus 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 log base 2 of 4. And there's 5 of them all together. So this would be 5 log base 2 of 4. Some other things that you probably want to remember about logs is how to evaluate them. So how to switch between logarithmic form and exponential form. So if we had 2 to the 3rd equals 8, we call 2 the base, we call 3 the exponent, and we call 8 the product. If I want to put this into logarithmic form, it would be log of the base, so it would be log base 2, and then it's of the product, so of 8. So there's my product. And it's going to equal, so logs always equal what the exponent is. So that's going to equal 3. So log base 2 of 8 is equal to 3. So what this expression is saying is 2 to what power would make 8? And that's what it's equivalent to. So 2 to the 3rd power is equal to 8. So log base 2 of 8 is equal to 3. So you guys go ahead and try this. Log base 2 of 8, it's saying 2 to the what power is 8. So see if you guys can evaluate that. We just did that. So why don't you guys try log base 2 of 1/4. So 2 to the what power would equal 1/4. You guys try that one. And you guys can try log base 4 of 64. So 4 to the what power is 64. So try that. And again, you guys can check your answers against the finished notes. So solving exponential and logarithmic equations. So let's say we have something like 2 to the 5x minus 1 equals 13. Well, does 2 to some power equal 13? No, 13 is not a power of 2, so I cannot change them both to powers of 2. So what you're going to do, if it's an exponential equation where you cannot rewrite the bases, we can put it in logarithmic form. So remember, it's log base 2, because that's the base, and then of the product, 13, is going to equal the exponent, 5x minus 1. Log base 2 of 13, you can use your calculator to solve this. It's called the change of base formula. You take the log of the product divided by the log of the base. So this would be log 13 divided by log 2, and this is going to equal 5x minus 1. So let's use Desmos to figure this out. So log 13, so we go to functions, miscellaneous, and then you've got your log function. So log 13, and then divided by log 5, I believe is what the other one was. Nope, it wasn't 5, it was 2. Yeah, log 2. So log 13 over log 2. And that's going to give us 3.700. So we're going to say that's 3.7. So this becomes 3.7 equals 5x minus 1. And then you just solve for x. So add the 1, 4.7 equals 5x, and then divide by 5. So 4.7 over 5 is equal to x. And you can use your calculator to get your decimal answer. That's how you can solve exponential equations. You can change it into a logarithmic problem and solve. If it's a logarithmic equation, so let's say we have log base 3 of x minus 4 equals 4, you would change it into an exponential equation and solve. So the base is 3, the exponent is 4, and that's going to equal x minus 4. Well, 3 to the 4th is 81, so 81 equals x minus 4. Add 4 to both sides, and x is going to be 5. For logarithmic equations, you need to be careful because remember the domain of logarithms, x has to be greater than 0. So whatever you plug in, when you take the log of it, it has to be greater than 0. So if I take 85 and plug it in, I would get 85 minus 4, which is 81, and that is a positive number, so we're good. If you get a negative number, then that is actually not a solution. So you guys go ahead and try solving these ones. On B, I would add 4 first, and then you have 7 times 5 to the x equals 14, and then divide by the 7 before you get started. So then you have 5 to the x equals 2, write it in logarithmic form, and then you guys can try. If we scroll back up to the 2 that we left from before, now we have a new problem, right? So if we wanted to solve 1,000 equals 10,000 times 0.8 to the t, we can divide both sides by 10,000. And then we would have 1/10 equals 0.8 raised to the t. At this point, we can write it 0.1 equals 0.8 raised to the t. Write it in logarithmic form. So log base 0.8 of 0.1 equals t. And then you can use your change of base property, log 0.1 divided by log 0.8, and that's going to give you t. So you guys go ahead and try finishing that. So how many years would it take to reduce those cases to 1,000? And how many years would it take to reduce it to less than 1? And then up above, approximately when did the population reach 50,000? See if you guys can go back and try that problem as well. Solve for the years on that problem. All right, we have not talked about e to the x yet. So e to the x is called the natural base. It occurs often in banking problems. Its e is approximately 2.71, etc. So it's like pi. It's an irrational number. It never repeats itself. The inverse of e to the x would be log base e. And log base e is the same thing as the natural log, and we call that ln. So log e, or the natural log of x, would be the inverse of e to the x. So if you want to solve e to the negative 3x equals 12, again, we don't know 12 is what. I can't change that to a base of e. So we are going to rewrite this in logarithmic form. So it's going to be log base e of 12 equals negative 3x. But again, log base e is the same thing as ln, so I can rewrite this as the ln of 12 equals negative 3x. And then we can divide both sides by negative 3. And so the natural log of 12 divided by negative 3 is going to equal x. And you have an ln button on your calculator that you can use, and you can just use it to solve. Log base 3 of x minus 4 to the 4th, again, we can rewrite this in exponential form. So this would be 3 to the 4th equals x minus 4, and you can just solve from there. When you have a natural log and an e back to back, that's like saying 3 plus negative 3. They cancel each other out. They're inverses of each other. So we're just going to be left with 3x. And so you would just solve 3x equals 12. Here's a log property we talked about before. I have two logs with the same base. They're both log base e's because they're natural logs, and I'm subtracting in the middle. You can rewrite them as a single log with division. So this is the same thing as the natural log of x divided by x plus 3 equals 5. And so this is the log base e of x over x plus 3 equals 5. You guys can solve that on Desmos, or we can write it in exponential form. E to the 5th equals x over x plus 3. And on this one, I would recommend solving on Desmos. So graph e to the 5th, graph x divided by x plus 3, and find their intersection points. So you guys can go over to Desmos and try that out. And you can look at the finished notes to see if you got it right. And that's it for today. So gentlemen, your homework again is out of the book. If you guys have any questions,